Welcome to a video on DeMoivre's theorem. We're going to look at it, do an example of it, and prove it. So the essential questions, Cornell Notes style, are how can we find powers of complex numbers in polar form? And the answer to that is we will use DeMoivre's theorem, and then we will go ahead and prove DeMoivre's theorem so we can use it legitimately. The way you use DeMoivre's theorem is by taking a complex number in polar form. So you have an r value, the distance away from 0, and you have a direction, which is determined by cosine theta plus I sine theta. So that's your complex number, and it's raised to the n power, any power you want. We take the power and we use it on the r value, so it's going to be r to the nth power, and then you do something a little different with the angle, and this will be proven in this video, so you'll understand why this works. It's going to be cosine, not a power, but n times theta, so the product of n times theta plus I sine, and again, n theta. So that right there is DeMoivre's theorem, and here's how you use it. I've picked a complex number in polar form with the r value of 2 and the direction of 5 pi over 6. If I was going to graph it, I did graph it. If I'm going to graph it, it looks like this. It's 2 spaces out from the origin, and it's in a direction of 5 pi over 6. And I'm raising that to the 10th power. Definitely not something I would want to do in a plus bi form, but easy enough in polar form. So the first thing I'm going to do is take the 10th power and use that on my r value, so 2 to the 10th power, and then I'm multiplying my angle. Multiply 5 pi over 6 by 10. That gives us a very whopping big angle of 50 pi over 6. In the cosine term and in the sine term. Okay, I have done the 10th power of 2, and that's 1024. And then I figured this was kind of big to work with, so I reduced it to 25 pi over 3. Still, that's a lot of wandering around the unit circle if you're going around 25 pi over 3 times. That's like 8 1/3 pi as a mixed number. So that means I'm going 8 1/3 pi around the unit circle. That's 4 times around the unit circle and then a little more. So what I'm going to do is subtract 24 pi over 3 or 8 pi from this. Those are all aimless trips around the unit circle where we start over again. And that makes a much simpler angle. So the answer to 2 cosine 5 pi over 6 plus I sine 5 pi over 6 raised to the 10th power is right here. We do have a big r value, but a very simple angle, cosine pi over 3 plus I sine pi over 3. We can also, if your teacher wants you to, we can also convert from polar form into rectangular form by remembering what cosine pi over 3 is. And I probably shouldn't have shown you that so soon. What is cosine pi over 3? I hope you know. And sine pi over 3? Cosine pi over 3 is 1/2, and sine of pi over 3 is square root of 3 over 2. So you can distribute the 1024 to each one of those terms, and it gets a little more manageable. 512 plus 512 times radical 3i. All right, that's an example of using DeMoivre's theorem, and now we're going to dive into the proof. So let me just reveal this a little bit at a time. The proof of DeMoivre's theorem can be done inductively by repeated multiplication. So what we're going to do is just raise to a very simple power at first, and remember the rules that we already proved from multiplication. So when we multiply 2 complex numbers, you multiply the r values, you add the angles. So I'm just going to keep it really simple at first and raise this to the 2nd power. That means that I have r cosine theta plus I sine theta times itself. Well, I'm going to multiply the r values. That'll give me r squared. And then I'm going to add the angles. And theta plus theta is 2 theta. Okay? Theta plus theta, 2 theta. That's it for the second power. Now, third power means I can take what I did in the step before. I already squared this complex number, but I need to multiply by one more r cosine theta plus I sine theta. And that'll give me the product of the r values, which is r cubed, and then I add the angles. 2 theta plus theta is 3 theta. So you're probably already noticing a pattern. I'll do it one more time. I'll do the fourth power and then we'll generalize. So this complex number, r cosine theta plus I sine theta to the fourth power, is equal to what came before. We already did third power, times another r cosine theta plus I sine theta. Multiply the r values, you get r to the fourth. Add the angles, you get 4 theta. And if we keep on going and try 99th power, I think you can see what's going to happen. It's r to this power, r to the 99th power, and then the product of 99 times theta goes in there in the body of the complex number. So then if we take it a step further and do r to the nth power, that's where we get DeMoivre's theorem. R to the nth power times cosine of n theta, the product there of n times theta and I sine theta. So that's the proof by induction, by looking for patterns and then generalizing. And the final thing that I want to do is summarize. So let's go to the summary. All you have to do to find wicked powers of complex numbers is raise r to the nth power and multiply theta by n. So when you're done watching this video, I hope you enjoyed it. After viewing it as many times as you want, I want you to try these 3 problems. I kept the basis pretty simple. I didn't go crazy on the powers, but I want you to try raising r to the power and multiplying theta. In each case, multiply your theta times the power, find that product, and then simplify the angles. Thank you for watching.